Okay, you can find these presentations, I think, on the sheet that's been sent out to you. And so I'll describe what this photo says. It's quite a spectacular photo, but it's hard to see here. This was some seismic data recorded in an estuary or an embayment in New Zealand. And we have many of those along the Oregon coast, and we have similar geological situations. What's shown on this, if you download it, you'll see there was an earthquake that went right through here, and there's a scarp that has several meters offset. In addition to the earthquake going through this person's farm, you'll see a big pile of sand over here that occurred coincident with the earthquake, and that's what's called liquefaction, and that was a sand blow that came out. So this farmer has fields made of small particles of sediment with lots of water, and there was a strong site response and heavy amplification that caused that sand blow. In fact, for me, an interesting historical note about that was when I came here in the early 90s, several times we went up to testify in front of the state legislature about the need for earthquake preparedness, and they sort of didn't want to do much about it. And they were digging a foundation for a building in Salem that was going to have many school kids go through it. And they called Ray Weldon up and said, hey, we see all these structures that look like roses coming up. And he said, oh yeah, that's liquefaction.
Wow.
And that's when Oregon started to change their building codes, because they realized they had more of a problem. So this is an aerial photo of this embayment. We're going to focus in this region here. I hope you can see there's some land here, water, and there's a town, much like an Oregon town, sitting there in that region. If you were to take a look at that lower Hutt Basin, you would see moving from the inland parts outwards that you went from relatively thin sediments or bedrock through a depositional environment where all these represent sediments laid down at depths of about 100 to 300 meters, right? So intuitively you know that if you had a 1 meter piece of granite and a 1 meter piece of jello, and you hit them both with the same input, the jello is going to move a lot more, right? Well, they put a seismometer array across that region and recorded the exact same earthquake at different points in that geologic structure. So this is reversed. Here's bedrock on this side, moving out towards the ocean. The magenta shows stiff sediment, right? And the yellow shows soft sediment. I think it's a really wonderful display of what site response means. Now, how many people felt the Woodburn earthquake? Do you remember the Woodburn earthquake in 1994? You felt it?
Yes.
Where do you live?
I lived on Augusta Street.
And is that where?
Just on the
Really,
side of
really?
the Laurel Hill Valley, heading up.
Oh, so you felt it on the hill.
Well, on the bottom side of the hill, on
Yeah.
the trough.
I used to live right down by the rose gardens, and I felt it. And over here in this neighborhood, up on the hill, nobody felt it, right? So there is a variation in site response just in Eugene for a magnitude 5 earthquake that occurred in Woodburn. And it occurred early in the morning, right? And I remember dreaming that the squirrel that would walk around on my skylight was so big it was shaking the house, and I was going to have to kill it that day.
I remember it. I got up.
Because I've been in Northern California in Humboldt County when there were like 6.5s, and I was outside at the time and didn't feel anything like at the beach or camping. But then I was in a basement in Fairbanks, Alaska, and there was some tiny earthquake, and I felt that. And so I'm wondering what.
So why did you not feel one, and why did you?
Yeah, I mean, does it have to do with how shallow they are, or being in a building versus being outside, or?
There's a whole series of factors that go into that. So let's list a couple. Remember the Loma Prieta World Series earthquake that occurred out in the mountains by Santa Cruz? Well, between that earthquake and North Beach in San Francisco, remember North Beach had lots of destruction. But in the intervening regions, not much. Yeah, Santa Cruz got hammered, and those communities in the mountains got hammered. But coming up towards San Francisco, not too much. Then you got to North Beach, and there was lots of issues. Well, two things happened in North Beach. One is, it used to be North Ocean, and it's all this fill that they put out there that's soft stuff. And the second thing that happened is that waves focus. So that earthquake sent waves down into the lower crust, and they focused off what's called a transition between crust and mantle. And it was like a lens. So the energy went down, got focused, and came up into North Beach. And you could actually see afterwards when people ran the models that there was a lens effect that focused the energy.
Did it go in a ripple? Did it look like that? Or did it look like a, did it have a pattern on the surface that?
It was
Ripple?
really, it was more, it wasn't so much ripples like a wave going by. Yeah, there was that too, but there was a geographic region that was distant from the earthquake that got more focusing like a lens going into it. There's similar events in Mexico, so that's those issues, complications of how waves propagate regionally, but also site response. So if you were, and what other issues could there be? There can be depth of the earthquake. There are nodal planes in earthquakes. They radiate energy irregularly. Maybe I'll show you a movie in a sec about that. So there's a list of issues. If you were a community trying to evaluate those, you would first say, am I on bedrock or am I on soft sediments? Then you would get more complicated. Let's see what more complicated might look like, and then I'll be quiet.
Should you be on sediments if you're at the, well, not necessarily.
Yeah, I mean, if you're on the beach, you know, that's pretty loose stuff, and you should feel it. So I'm not really sure in that particular case what to say.
It was like sand.
Sand, yeah. How distant was the earthquake?
I do not remember anymore. And they felt it in Arcata, and I was just outside of Arcata. I don't really know.
And what did they feel in Arcata? Really heavy rumble or a sharp jolt?
Things fell off the shelves.
Oh, yeah.
That's all the thing, since I didn't feel it.
Yeah, I don't know.
I was in the East Bay for the Loma Prieta up on a hill, and we went out to the parking lot, it was long enough, and watched it undulate.
Oh yeah, that's
through our
awesome.
parking lot.
That's cool.
I would pay for that experience. Yeah, I've studied seismology for a long time, and I've only felt a few earthquakes. So, maybe I'll become like one of
Live
these
on the wrong.
tornado hunters or something in the future. I'm just going to finish with this movie if it plays. It's also in the PowerPoint. This is for the 1906 earthquake. And you can see it in decent light. You're seeing the ruptures proceeding. It's moving north and south. And you can see the intensity of ground shaking is not a simple pattern, right? There's strong ground shaking moving off in that direction, certainly strong as the fault's ripping in this direction. And the fascinating thing about these large earthquakes is they take a long time to play out. A magnitude 9 earthquake that would rupture from Vancouver to Cape Mendocino would take about 3 minutes. And that's a long time.
So why is Santa Rosa having such a strong response? I mean, is that what the red is, the stronger?
Exactly. So it's shaking intensity on this. I don't know the exact reason, but what they've done now for California and these regions is they've taken detailed geologic maps, so not just local site response, but what they put into these models are the very detailed geology in the subsurface. So not only does it matter what's right on the surface, but how can things focus or defocus because of the structure at depth. So they've done this for San Francisco, they've done it for LA. I don't know if any of my grad students know more about this than I do. That might be from the California area. But that complexity you see in the movie is the interaction between the earthquake occurring and all that geology they put into this model. So Santa Rosa, my guess would be, let's watch it. Is there something, local in that model? You can see now it's building up. It's,
Yeah.
There's kind of a delta along there, I'm just trying to.
It
think
looks
what's-
like there's a river.
Well, there's a delta that goes in, Petaluma and stuff.
Yeah, there's a river over there.
in through like this.
Yeah.
Yeah, but you don't see it so much here, but you do see it there. I'm not really sure what caused that.
Good question. But there's a mountain range, that dips down in Santa Rosa, it's like a valley for that matter.
It's in that red spot.
Yeah. Santa Rosa in a valley?
Yeah, because between that falls and Santa Rosa is the Coast Range, whatever you call that, those hills, the Petaluma Hills.
Any valley is going to be a receptacle of sediment.
Yeah, it's a valley.
That's a valley, it's definitely
So
a
it has
valley.
it effectively has a thicker pile of sediment that's responding to that. Okay, so I'm going to stop there. What we'd like to do,
Yeah, so Napa got not.
sorry, that's great. No, go ahead.
No, she was just saying, there's the Napa Valley that's between Santa Rosa and that delta. And it didn't
That's
appear,
right, you know, it's
it didn't appear to have any. So it's an interesting question.
No, it's a good question. Don't know the answer.
So I think we're going to break up into two groups now, those who need ice cream sooner and those who can handle it later. And roughly halves, if that's possible. And the first, the more ice cream needy group should go outside, right? And-
Yeah. And what we have set up here is 3 stations to sort of work yourselves through. The students are going to help you through this. It starts on the table in the back, and they'll explain it, and it goes this way. 1, 2, and 3. You end up with the Slinky seismometer and this old 3-component seismometer. And then the other half can come outside, and we're going to work.